we will be studying about the calculation of slip ring or wound rotor resistance. Cal.
So still I have joined. So
No, no, I'm not. I'm not continuing. I'm just writing the topic. Calculation of slip ring or wound rotor induction machine. Okay. Before moving to this particular part, so I'll just briefly review. Let the people join, so it will not affect them. These are the things which we have already studied previously. So if you have to draw an equivalent circuit of an induction motor, so here you will have a resistance, here we have reactance, and this is the shunt magnetizing branch. Over here we have a resistance, over here another reactance, over here now, and down it's the and then here we have again a reactance, a resistance, and here we have a load resistance. So if you notice for the transformer, this portion is not there. Okay, that's why we called an induction motor as a rotatory transformer also. So you have the stator side current here, this is the stator side, this is rotor side resistance, this is rotor, sorry, stator side resistance, this is stator side reactance, this side is the stator side, this from here we give to supply basically. Okay, so this is the stator side, then here we have this. Okay, current I naught. What is this current I naught? This is the no load current, and this current excites the induction motor. And from the resistance, there is a loss component of the current that follows. From the reactance, there is the IM, that is the magnetizing component of the current. So here we can write R naught, okay, X naught, or some books will write this as XM. So here we have the rotor side. Okay, here we have the stator side resistance, and this is the load part of it. So as of now, this is the induction motor. No one has joined till now, huh? No, people are joining. Yeah. So as of now, if you see over here, when I'm drawing this particular circuit, so I can notice my values. What is RS? RS is nothing but, huh? It's looking good. RS is nothing but stator resistance, stator resistance per phase. Okay, and your axis, no, wait, I am trying with different backgrounds. Graph, blue line will look good. No, this is good. uh, yeah, this is good. Axis would be your stator reactance per phase, stator reactance per phase. Okay, similarly you have your this these all the values are in ohm, and you have your RR dash, that is your rotor resistance per phase. Why we are writing this dash? Because we are referring it to stator side. So when we are referring the resistance, so we know the formula is that for reference we have this E S by ER. Okay, in a transformer E secondary, so see, by we can write IR by IS is equal to A. Okay, so once we are referring one side to the other side, so we know from the transformer equations only. If you, for example, will write VP by VS, okay, is equal to IS by IP. Okay, here instead of NP, that is number of turns, we write TP by TS. Okay, so here you just analyze one thing. I just want to show you so that you don't get confused. Suppose you want to write IP. So IP is how much in terms of VP? It is VP by RP. Okay. Now IP is VP by RP. You know that IP is VP by RP. But here, if you want to write this IP here, so IP would be equal to IS, okay, into Vs by Vp. Vs by Vp. So just now we saw that Vp by Vs is given by a constant A. So we can write Ip is equal to Is by A. Is by, because this is the inverse of this, Vp by Vs is A, Vs by Vp would be Is by A. So if I want to write this in terms of Ip, so how I can write Is by A is equal to Vp by Rp, or in other terms I can write Is is equal to similar. These are the things that we have to substitute there. And if we will be knowing that if we are referring to the primary side, then we have to divide by A square. If we are referring to the secondary side, then we have to multiply by A square. The reason being is this particular thing we have to substitute. Now you just saw that Is is equal to Ip is equal to Is by A. Is by A. Now similarly, if you want to write now this Rp over here, Vp by Rp is equal to Ip, and Vp by Rp, we just now saw that Vp by Rp was equal to Ip was equal to Is by A. How it was Ip was equal to Is by A? Because Ip by Is, sorry, Is by Ip was equal to, here I'll write down, Is by Ip was equal to A. In other terms, your Is is equal to AIP. Is is equal to AIP. From here you can write Is is equal to A times Ip. Okay, and your Ip is equal to Vp by Rp. So Vp by Rp is equal to sorry, here there is a mistake, that's why I was wondering. Vp by Rp is equal to A times Is. Vp by Rp is equal to A times Is. So that means if you want to express like in terms of primary, so you have to divide by A square. If you do the further calculations, you have to divide by A square. If you have to refer it to the secondary part, means you have to express in the next slide. Here there's no this thing, you're getting confused. So here I'll just start. So see here, Vp by Vs is equal to Tp. Instead of Np, I'll write Tp by Ts is equal to Is by Ip is equal to, let's say A, some books will write K, whatever it is. So here if I want the value of Ip, I have to write it in terms of Vp by Rp would be my Ip. Voltage by resistance would be my current. So here now I want to express this. Is would be equal to Ip A times Ip. Now suppose I want to change this all the values in terms of secondary. I want to refer primary to secondary. So I want to see Vp is equal to, from here Vp is equal to A times Vs. Okay, A times Vp is equal to A times Vs. So if I want to write all the values in terms of Is, okay, all the values, or if I want to write instead of here Ip, if I want to express this Ip in terms of Is, so how I'll write Ip is equal to Is by A. So here I'll write Is by A. Okay, here Vs Vp, I want to write it would be AVs. Okay, and Rp is as it is, Rp. Now what I get is now if I want to write Rp, Rp would be equal to, I cross multiply, Rp would be equal to A square Vs divided by Is. Now Vs by Is is nothing but Rs. So I can write my Rp is equal to A square Rs. Okay, got this point? Similarly, I can write Rs. If I have to refer to the secondary, I can write Rp by A square. So these are the two things that I wanted to explain you. And on the similar concepts, you will get your excess, your xp is equal to A square xs, and similarly your xs is equal to, if you want to write in terms of that, xs is equal to xp by a square. Just wait 1 second, my battery is down, I'll just power it. Yeah. Yes. So Ratika, you got? Hmm? Hello,
Yes, sir.
are you getting this point? You got my
Yes,
point,
sir.
what I'm trying. Oh yeah, yeah. So this is elementary, this you have studied in the before also, but it is very vital because I have to do this referring now when I'll be starting my this thing. So this was for the understanding part. So how we refer, it's very simple. So let's yeah. So let's now go for the understanding. Now the resistance you can write in terms of rotor side resistance, that is RS. You can write rho L by A. So resistance of length. Suppose you have length will determine, you cannot calculate only for the length but the total number of turns. For example, you have 10-meter wire, okay. You have a 100-meter wire, and one turn is carrying 10 meters. So the total length of the wire is 100 meters because the total number of turns are 10. So when you are calculating the resistance, you have to account for rho L by A into the number of turns, which I have already told you in the beginning. So when you will be calculating this, it would be rho LMTS into TS by AS, which we have seen previously also, this multiplication, because you have to account for the entire length. So when you have to go for this calculation of the rotor resistance, stator resistance per phase, so you have to account. So where the value of rho usually is a specific resistance for stator winding, it's in the range of 0.02 ohm per meter per millimeter square. In the previous numerical last day, yesterday we solved, it was like the same value. So LMTS is what? It is the length of mean turn for stator winding. This is the length of mean turn for stator winding, and then you have your TS, that is the number of stator turns per phase. TS is number of stator turns per phase, and then you have your AS, that is nothing but the cross sectional area, okay, of stator conductor, that is in millimeter square. This is cross section of each stator conductor, it is in millimeter square, okay. So now if we have to go for the calculation of the rotor, similarly like rotor, we can directly write rho LM TR divided by AR, okay. Rest all the things will follow. So now if we have to refer like slip ring rotor resistance per phase referred to stator side, so we are referring to the stator side. So how do we refer? So here we are referring to the, therefore see, slip ring rotor resistance refer to stator side. So in order to refer this to the stator side, so how do we go about this? It's becoming out of proportion. So how do we refer? Simple. what we do is we have to take our RR dash, which I showed you in the previous class. Oh, sorry, here you see this RR dash is there, na? So this is R. Why dash is there? Because this resistance is referred to the stator. So if RR has to be referred to the stator, that is rotor side resistance. See, the secondary has to be referred to the stator. So what we do? Primary resistance we divide by A square. Okay, it can be any variable. Here some books say A, K, or X, anything. It can be xs xp by x square also. So okay, so this was for your understanding. So here RR dash, if we have to write, so we have to write this RR, okay, divided by x square. Okay, where our this where your x value or k value, whatever value you are taking, this x value here, for example I have written x square, I can write a square also. Okay, where a value would be equal to your er by es. Okay, so this thing he has taken. So this x square value can be also expressed in terms of see t see er is directly proportional to the kwr and number of turns, because e formula, if you see, it is 4.44 f phi, okay, kws ts, so it is directly proportional to these terms. Similarly, er would be directly proportional to these terms. So in other words, we can write that your rr would be equal to x square. X is basically the proportion of these two, tr kwr divided by ts kws whole square, which can be further simplified, like rr dash can be written as ts by tr, okay, into kws kwr by whole square, because I have reversed it, so that into rr. So this is like referring style. Now let's go for understanding the calculation of squirrel cage rotor resistance per phase. So we have to study how to calculate the calculation of squirrel cage rotor resistance per phase. Calculation of squirrel cage induction motor rotor resistance per phase. Now, if we have to understand this, so what we will do is that first of all we have to understand the copper loss. Okay, copper loss in the rotor due to bars and end rings. So we have to account for the copper loss in the rotor due to bars and end rings. So already we have figured out in the previous class what is the copper loss in the rotors. So copper loss is because of the bars. Copper loss due to the rotor slots was studied. So copper loss due to SR, that is the rotor bars, okay, we just saw was equal to SR, okay, IB square, instead of here rho LB, okay, into AB, that we saw in the previous class also. So this would be the copper loss, and this copper loss is in watts, okay, and resistance of each end ring also we saw that, and copper loss due to each end ring also. See, resistance of each end ring, resistance of each end ring. So if we have to go for the resistance of each end ring, so I told you the resistance would be pi instead of L. It's a circumference, so it would be pi dE, that is 2 pi r. Okay, you can write pi dE by AE ohms. Okay, and now also the other thing is that because you have two end rings, so you have to account for both the end rings. So now this is the resistance, then the copper loss due to both end rings, top and bottom you have two end rings, so you have to account for both the end rings, would be twice, okay, twice end ring current, that is IE square, into a resistance, that is rho pi dE by AE. So this be equation 1, 2, and 3. So now what you have to do is that copper loss in the rotor due to bars and end rings. So bars and end rings means this plus this. Okay. So you have to account for copper loss. Next slide will go. So copper loss due to bars and end rings. So if you have to account for the copper loss due to the bars and end rings, so that would be equal to SR IB square rho LB by AB plus your 2 times IE square. Okay, then rho pi DE AE, and this is in watts. Okay, this is in watts. So other factors, now you have to simplify it. So what are the common things? So you can take the entering current. You have already calculated the value of this entering current in the previous class. IE was equal to nothing but as SR IB by pi P. Okay, you have studied pi P. So this is your equation 3. Okay, let this be equation 4, and this be equation 5. So substitute 4 in 5 the value of this IE, so you will have a different expression. So please calculate this expression. Yeah, you should be able to calculate the expression and tell me what values you are getting. So if you will recalculate the expression, so you have to write now, you will be having your, instead of you will be having SR IB square. Okay, so this thing will not change. Rho LB AB, instead of here twice, instead of I you will write SR IB pi P whole square. Okay, here. So this term whole square into the same thing, rho pi DE AE. Okay, so there are some commonalities that you can see over here. So what are the terms common? So SR IB square here. Here also you can see SR IB square. So although it is SR square IB square over here, so what are the things that you can take common on both the sides? Okay, so you just carefully see what are the things that can be taken common, and take these things common, and see, as far as I am concerned, I can see SR IB square rho LB AB plus 2. You can take pi outside. Okay, 2 pi square is there na, so this pi square and 1 pi will get cancelled, this pi and this pi, because this pi square, so only 1 pi will remain. So this pi remains over here, so I'm just writing in the equation. So apart from that, you can write this as again SR IB square rho LB AB plus 2 by pi. Okay, 2 by pi into rho, this value rho SR square. You can write rho SR square IB square, IB square. Okay, into DE. Okay, DE by AE. Okay, DE by AE, and here what is here, P square. Okay, that P square will come here, this P square. So you have this equation over here. So now you can take common. Can you take common and tell me what are the values? You can take common rho. You can take common your SR square. If you want to take common, you can take SR square IB square. Okay, so if you are taking SR square common, so what you have to write here, instead of LB you have to you have to divide by SR also. So what you will do, this particular value, this over here, this value, this equation, uh, I'll just write this be equation 6, because in this, so what I'm trying to do, So in this particular equation, uh, what you do is you take SR square, okay, your rho and your IB square, okay, IB square common. So once you are taking this common, so here it would be LB AB. Since you have taken SR square, so you have to divide it by SR, okay. So that is the thing over here, and rest other things will follow. That is your 2, okay, 2 2 by pi, 2 by pi will remain, yeah, 2 by pi will remain as it is. So rest things you have to write the DE, okay, DE other value would be down, that is P square AE. So this is the equation you will get. I'll write in the next page. So are you following, Ratika? Ah,
Yes, sir.
okay. So any doubts? So you please let me know, because this is very important. It comes in the examination also many times. SR square, IB square. So I've taken this common. I'll write this equation. I Because it's not a blackboard, I have some limitations. SR AB. So people, uh, yeah, all of a sudden I'm getting this noise. In why is it? Uh, okay, it's due to my, okay, I got it. It's due to my phone. Okay, no problem. So yeah, so we have this value. So we have the final value. So we can write our this thing, LB SRB plus 2 by pi into DE rho square AE. So this is in watts. Okay. Now one more thing is that if you want to, like, this is for the total copper loss. Okay. Now if I want a resistance of the rotor due to bars and end rings. So if I want the RR value, okay, due to bars and end rings, so what I'll do is that I came to know this is the I square R loss. Okay. Only thing is that IB value I have to, like, eradicate. Okay, because basically what was copper losses, okay, copper loss is I square R loss. So only quantity I over here is this. So if I eradicate this value, so the rest of the value is for resistance only, na. So this is rho SR square LB, okay, SR AB plus 2 pi DE, okay, B square AE. Okay, so this is in ohms. Now if I have to, like, refer this resistance, that is RR dash, I have to refer to stator. So I'll die RR by, okay, X square, okay, where my X would be equal to ER by ES. Okay, so if I want to refer this value, so previously also you have seen RR how I have done. So I have directly can write RR is equal to M, okay, TS KWS, okay, this is MS, this is MR TR KWR ka whole square. So this is I can write here, instead of X square one step I missed, where I can write RR, okay, here let this be our equation, it was equation 4, this was our equation 5, okay, this is our equation 6, and this be our equation 7, this equation 7. Okay, so let here you can see that RR, I directly wrote this. So you can divide this RR X square, you can divide, that is, you can write MR TR KWR MS TS KWS, this is the whole squares. Then you come to this step. So now you will assume, let's assume MR value to be equal to SR by P. Okay, and tr and tr, this is the tr is equal to p by 2 and kwr is equal to 1. This is for squirrel cage induction motor. Okay, squirrel cage induction motor, this is a primary assumption. If we are putting these values, why are we putting these values? So we have to know how many like slots are there per pole. So and usually the number of poles would be equal to the number of slots as far as the turns are concerned. So turns would be like half of it, and kwr is the winding factor, which already we have seen. We take it to zero point 0.9, but to make the calculations little easy, and that's why we have taken. So we can write rotor resistance referred to stator side. So now rotor resistance referred to stator side. So when we are referring this, so rr dash would be equal to ms ts kws. Okay, whereas mr we will be giving the values of sr by p. So we are giving the values sr by p, here p by 2, and here the value is 1. So these values we are putting over here into our normal value which we got over here. This is the resistance value which we got. So this value we will be substituting. This is the resistance value, rr value. So from equation 6. Okay, this is equation 6. Okay, substitute, we'll write down. Okay, here substitute equation 6. So what is the equation 6? So equation 6 over here, it would be rho s r square, okay, into what is that, ib is there, rho s r square, what was that, rho s r square lb. Okay, lb sr by ab, plus 2 pi plus 2 pi into d p square ae. So this value we will substitute here. So when we will be re-substituting, so this is whole square, so this will become p by 4. So this 4 will come over here. So we can write 4, okay, ms square ts square, okay, kws square, okay, then sr by p. Okay, so 1p, yeah, yeah. So now 1p will go. Wait, I have, so you tell me the value, what values you will get, what is the final expression that you will get. So 1p and 1p gets cancelled, okay, because this is sr by so this sr by p, and here also you have while you are substituting there, so you p and p will get cancelled, so no problem over there. So 4 will come up. So here you have a p square, so you can write that p over there, and yeah, p, okay, yeah. So no, p will get cancelled. Okay, so you are left with the row. Okay, the row value, here pp gets cancelled, you are left with the row value over there. So take this row value, in the down you have sr, only sr is left. So sr, so sr is multiplication with these two quantities, so you are left with um, the down there it is sr, so you have to, this is sr square. So and it is there, so that sr square you have, you can take out there, row lb lb sr ab, okay, plus 2 pi into d p square into ae. So this is mostly how do you go about it. So this SRAB was there, so this SR square, uh, this SR square here, this SR square and this SR square will get cancelled. So we are left with only, and this P gets cancelled, this becomes 4, this comes here, 4 ms square ts square kws, this row is there, row remains outside, lb is there, lb is there, srab whatever it was there, it was plus 2 pi plus de rho square pi, okay, rho square ae, rho square ae. So the final expression which you are getting, you are understanding, huh? Yeah. Noor, are you following? Noor,
Yes, sir.
are you following any doubts? See what
No,
you
sir.
have,
No doubt.
you have to sit with the copy, okay? See, I have to clear myself only. I feel like I'm teaching my own self. So you have to in between, like if you're not getting, you please, okay. So this is RR dash. So this RR dash would be equal to 4 ms, okay, ts square kws square, okay, rho, and finally lb sr ab plus 2 pi into d rho square into ae, and this is in ohms. Hello, are you there? Yeah, I'm sorry, little. Hello?
Yes,
Yeah,
sir.
can you listen to me?
Yes.
Ah, there was a power failure, so just I just got to start my generator. Okay. So here, this is the final expression. Okay, now you can see the screen. Hello?
No, sir. No, sir.
Okay, I'll.
No, sir.
You're not able to see. Okay, no problem. So power failure because of that. Yeah. Now you are able to see. Are you able to see the screen?
Yes.
Okay.
Yes, sir.
I'm really sorry. Inverter suddenly went down, so I had to switch on the generator. So this is the final expression. Now if you substitute the value of ms, that would be equal to 3. So then you get this rr dash would be equal to 12. Instead of ms you can substitute 3 because 3 phase network. Ts square kw s square rho lb, okay, sr ab plus 2 pi de, and this your p square ae, and this is in ohms over phase. Okay, let's do one small problem, okay, in, which has come in the examination. So let's see. Yes, yeah. So this is the final expression in the examination. What you have to do, derivation is okay, but keep these formulas in your at your fingertips, because it would be very easy. Suppose a numerical comes, so you need not to derive that. If you remember these are the values, you can directly substitute. Okay, so this is the way to go for the examination scenario. Now see, uh, this background is good, huh? This one or this one is good? Which one you like? This one? You tell me. Which background you? This background is okay, or this is okay? This one is okay. Ratika,
Sir.
Noor, which background is okay? This one?
Sir, the previous one was good, sir.
This one?
Yes, sir.
Okay, so we'll follow this one. Okay, so the problem is calculate the equivalent equivalent resistance. Calculate the equivalent resistance of rotor per phase of rotor per phase with respect to stator, with respect to stator, the the current in each bar and ring, the current in each bar and end ring, and total copper loss for a 415 volt 50 hertz 4 pole 4 pole 3 phase 3 phase induction 3 phase induction motor 3 phase induction motor having the following data. So this is the data you have. Data stator slots is equal to stator slots is equal to 48. Okay, conductors per slot conductors per slot is equal to 35. Okay, current in each conductor, current in each conductor current in each conductor is equal to 10 amps. Okay, current in each conductor is equal to 10 amps. Your rotor slots is equal to 57. Okay, length of each bar, length of each bar is equal to 0.12 meter. Okay, area of each bar, area of each bar, area of each bar is equal to 9.5 into 5.5 millimeter square. And your mean diameter of end ring, that is dia of end ring, de, is equal to 0.2. Area of each end ring, that is your ae, is equal to 76 millimeter square. Okay, resistivity of the copper, that is resistivity of the copper, is 0.02 ohm per meter per millimeter square. Full load power factor, that is your full load power factor, is equal to 0.85. So this is the problem, this is the given data they have given from given data. Okay, so now you have to calculate the equivalent resistance of the rotor. Okay, rotor per phase with respect to the stator. So you have to calculate, what you have to calculate exactly, you have to calculate this value. Okay, in order to calculate this value, you require certain factors. Okay, so first of all, when we are solving this particular problem, so what stator turns per phase we should know. So in order to get the stator turns per phase, so we know how many number of slots are there. So it is telling us stator slots are 48. And how many conductors are there in the slot? So the conductors there in the slot are 35. So we know that the ZSS value is 35. Okay, and SS is equal to how much? 48. So how much would be the total number of conductors? ZS would be equal to SS into ZSS. So that means total number of conductors would be 35 into 48. What about TS? TS is nothing but 6 times ZS. Okay, for three phase. So ZS would be equal to TS by 6. So TS by 6. So if you have to sorry, Z, no, sorry, what, where was I? TS is equal to, sorry, ZS is equal to, mistake over here. Yeah. So your number of turns, so your ZS, basically your number of conductors, your ZS would be equal to 6 times TS. So that means 35 into 48 is equal to 6 times TS, or TS by 6. So from here you get the value of TS. So you are getting the value of TS around 280 after this calculation. Once you got the value of TS, it is very easy. You can get the value of bar current. So the bar current value, you know, that is equal to 6 times TS kWs. If it is not given, I have told you, you will substitute 0.95. Okay, and you have IS. Okay, cos phi, and this is your SR. So you substitute the value, so you have the power factor, you have everything. 6 into 280 into 0.955. Your current in each conductor, that is also given 10 amperes. 10, your power factor is also given 0.85, and the slots in the stator are also given 57. So you get your bar current. So the bar current, you'll get around 239.3 amps. So once you get your bar current, so it is not a big thing. You can easily you can easily calculate your end ring current. So you can calculate your end ring current. End ring current is what? SR into IB into pi p. So SR value you already know. SR value is how much? You tell me. SR value you have to substitute, that is 57 into IB value that you just now calculated, 239.3. 239.3, and pi value is there, 3.14, and the number of poles is 4. So you get your end ring current also. The expression for end ring current, you will get around 1086 amps. Okay, so if you will be doing, so you it would be around this. So now you have to see the rotor resistance. Now the rotor resistance, that is the resistance of each rotor bar, RB. This is RB would be rho LB by AB. Okay, rho LB by AB. So rho value is given 0.02, LB value is also given 0.12, AB is given 9.5 into 5.5. So you get this around 46 into 10 power minus 6 ohms. Okay. Now you have to go for the I square R loss in a rotor bar. So this I square R loss is IB square RB into SR. So these things you have to take into account. So once you have to take into account, so you'll substitute these values. So once you substitute these values, you get around 150.15 watts, because all the values you have IB, SR, IB, you substitute there, you will get this. Now resistance of each end ring RE is equal to what? Rho pi DE by AE. So rho value also you have, okay, 0.02, pi value also, 3.14. This is DE given 0.02, okay. So and then other values is also given, AE value 0.95 into 5.5, so you get this value around 165.3 in 10 power minus 6 ohms. Now in both the end rings, if you want to see the end ring loss, so you can 2 IE square RE, and these values you can substitute. So IE square also you have, RE square also you have, IE square from here you have IE square, RE square, you substitute these values, you get around 390 watts. Okay, I want you people to do this problem. Okay, and then we have this what I call, so when you get these losses, so total copper losses, so total loss would be equal to 150.15 plus 390. That is this is in the bars and this is in the end rings. So this is the total copper loss. Okay, so total copper loss would be around 540.15. Now equivalent resistance we have to calculate. So equivalent resistance RR dash would be equal to 4 ms TS square KW S square rho I, this LB SR AB, this is LB, okay, LB plus twice DE by pi P square AE. So here you can substitute, that is 4 into ms is 3, TS value we calculated 280 whole square, KWS value is given, sorry, 0.95 whole square, rho value is given 0.02, rest value 0.1257 into 9.5 into 5.5, this is the area, plus 2 pi into DE value is given 0.2, number of poles are 4 ka square into AE value is 76. So when once you substitute in this expression, so you get this value as I was a little fast, you will get this value as RR dash is equal to 2.5 ohms. So if you see, calculate the equal resistance with respect to the stator, the current in each bar. So see, this thing, this expression, if we wanted to go directly for this, only we needed this value, TS value we had to calculate. Rest all the values are there. DE value is there, AE value was there. So directly we could uh, go for this, but they have also asked for the other factors. Okay, calculate the equivalent resistance of rotor per phase with respect to stator, the current in each bar. So he's asking for bar current, so IB. Okay, and end ring current he was asking for IE, and total copper loss also he for. So this question has came in the examination recently, 2020 or 19, something like that, for 8 marks. So I felt this is important, so you go through this problem. So now we'll conclude the class here, so please give your attendance. Yeah, please give the attendance. I'm sorry for the that delay. I'll stop recording the session.